Hey, Keaton, great to see you here. Josephine and Tiffany. We're going to do the meat and beef question for the hot dogs for chapter 17. Josephine has a question too. A man goes to new cities and has 2 routes. That's a good one, Josephine, right there. We'll do that question here next. Lots of great stuff. Got some Pearson ready to go. How's everyone doing? Keaton, great to see you. Josephine and Tiffany. Let's see right here. Loading everything down. Got a little bit of lunch. And re-waking up Mubot. He's breaking the world behind us. I think we're streaming. I think we are. Maybe we're not. No, it's just streaming. 9 kilobytes, 9 megs up a second. Can you go into greater detail on part A on the question? I'm good. Doing well. Doing good today. We'll go into greater detail on part A of the question. Let's see right here. Project 2. This is my last semester. Ryan won't be able to join any more lives. Keaton, you can join anytime. You can join in. You can say hey. You can swing by. We can go out, throw out 100 points. Mubot gives out the points. You're always welcome to swing by. Once we're back in person again. Do I not? There it is over here. Once I'm back in person on campus, people can swing by the office and say hey. I miss those days. I miss people just swinging by and being like, hey, Brian. Especially former students swing by. It's really nice. It's so interesting. Like a student will walk into the doorway, and I'll be like, "Oh hey," or they'll be like, "So and so was walking around looking for you, Brian." I'll be like, "Oh really? I haven't seen them in forever." So awesome. Let's check out this question here, chapter 17. Here we go. So this is a study on beef and meat hot dogs, and we made an 89% confidence interval. That is the weirdest confidence interval ever. I don't know if anyone makes 89% confidence intervals. Let's know we're good. Maymester. Oh yeah, of course. Yeah, you were part of the mini term. Yeah, Keaton, totally, dude. 100 points. We got new stuff. We got so many new things. I'll show you a new thing. Hang out for a minute. I'll show you a new thing between here. It's one of my favorite new things we've created. But we've got Mubot and so many more things. You were part of the inaugural Stat Nation group that we created Mubot with, and Mubot barely existed back then, but you were part of the original Stat Nation. And people don't know this, but Stat Nation was created by that class. They started calling themselves Stat Nation. So yeah, it was Maymester 2019. They created Stat Nation. Or 2020, Maymester 2020. I'm losing track of time. That's fun. Okay. So this interval right here, if you look at this interval, now here's the important things to note. So I won't solve the question for everybody, but take a look. With this right here, this interval right here, so it might be inverted. When we do this, let's plug in some numbers right here. If the mean for meat is something like 10 and the mean for beef is 4, then what would these numbers solve out to? If it was 10 minus 4, what would this interval solve out to? If it was 10, if the mean for meat was 10 and the mean for beef was 4, what would this interval solve out to? If the mean for meat was 10 and the mean for beef was 4, it would solve out to 6. So at this point, for my interval, the whole interval here is positive. Now make sure you see for my interval. We'll see. Make sure to check yours out. Yours might be different. My interval is completely positive. So that would make me think I have evidence which mean is higher. If my interval is completely positive, which my interval is, I would have evidence which of these is higher. My interval is completely positive. So yours is different. But if beef was higher, it'd be like 4 minus 10. And then what does 4 minus 10 solve out to? If beef was higher, it'd be like 4 minus 10. We're talking theoretically right here. Let's bring up some Epic Pen right here. So 2 seconds and load up Epic Pen. It's going to cause issues on my computer, but that's all right. We'll deal with it. If beef was higher, then right here, we would have 4 minus 10, and then it would solve to what? If beef was higher, then this would solve to what? If the true mean for meat is 4 and the true mean for beef was 10, it would solve to negative 6. But that would give us a negative interval, right? If the second one is higher. But if the first one is higher, the interval would be what? If the first one is actually higher, the interval will be negative or positive. So if you solve this out right here, now this doesn't solve to the interval, we're just talking theoretically. If the first mean is higher, we would expect the interval to be what? If the first mean is higher, we would expect the interval to be what? If the first mean is higher, we'd expect the interval to be what? Saying here's what I think the difference is between these. If the first mean is higher, Well, it's not what we want. If the first mean is higher, then the interval will be what? If the first mean is higher, then the interval will be what? If you solve this out, then the interval will be what? Like positive or negative? If we solve this out now, the interval will be what? If the first mean is higher, which it is right here, the first mean is higher, theoretically speaking. If the first mean is higher, it'll be positive. Great work, Tiffany, right there. It'll be positive. But if the second mean is higher, like theoretically, then the interval will be what? If the second mean is higher, then the interval would be what? So we have a few instances right here. The interval could be negative, and that means we think that the second mean might be higher by that much. The interval could be positive, and then we think, oh, it should go lower number to higher number. The interval might be positive, and then it might be the instance that the first mean is higher. Or what number is contained in this interval right here? In this interval right here, what number is towards the middle of that interval, which could be what you have? What is in the middle of that interval right here, the one I just wrote with the star? What value is in that interval? That means there might be no difference. An important value to see that's in this interval, which means maybe there is no difference between the means. Because it could be negative, it could be positive. So with this interval right here, 0's in there. 0 is in there. And 0 would mean that maybe there is no difference. Because maybe it's that the first mean is higher by this much, maybe the second mean is higher by this much, or maybe their difference is 0. Maybe there is no difference between the means. Because the null hypothesis for this test is that the true difference between the means, mu1 minus mu2, is equal to 0. So tell me with this. Is it possible that the difference is 0? If this is your interval, is it possible that there is no difference? Is 0 contained in the interval? So if 0 is in the interval, that's a possibility, right? So you would not reject the null, and we could not tell the difference. But my interval is a bit different. I'm trying to estimate what the difference are between these means. Now, these are not the means. This is an interval estimating the difference between them. These are not mean 1 and mean 2. We're saying, I think the difference between these means is somewhere in this interval. So if we were to talk about like Brian versus Darren playing basketball, we might say, well, Brian and Darren are going to shoot 20 free throws. But I think the difference between Brian and Darren is somewhere in this interval. And we might do true mean for Darren minus true mean for Brian. So if we did this right here, what does this interval mean right here? This is a very important conceptual thing. It's like this interval here. But if you were to do Darren minus Brian right here, and you got this interval, and we take 20 free throws and we see how we do, then what does this mean? What are we trying to measure right here between Brian and Darren and their 20 free throws? That on average, what? What would 2 through 5 mean? I'll explain in a second. So what would 2 through 5 mean if Brian and Darren are taking 20 free throws, and we're saying that the difference between... What would it mean? What would this 2 through 5 interval mean? So 2 to 5 is the interval. 2 to 5. I'll put a comma there like they do, so it doesn't look like a negative. But 2 to 5 is the interval for when Brian and Darren take 20 free throws. So if the interval is 2 to 5, we're trying to estimate the true difference between Brian and Darren. Hey, Jacob, good to see you here. So if we're trying to estimate the true difference between how many free throws Brian and Darren can make when we take 20 free throws, then we'd believe what right here? We'd believe what? And so this will go towards your question too, Tiffany, here with the second part of this. So if the interval is 2 to 5, when we estimate the true difference between Brian and Darren, well, so look, with this interval right here, we have Darren is taking free throws, and we're seeing on average how many free throws does Darren make. And then Brian is making free throws. On average, how many free throws does Brian make? And then this is the interval to estimate their difference. So what does this interval mean? This interval right here, 2 to 5, is what right here? What does this interval mean in context? So what does this interval tell us about this? Like, what does it mean when you say the interval right here is 2 to 5 for whatever we're measuring? Who can help us out with that right there? What does that interval mean? What is it trying to measure? So what are we trying to understand about Brian and Darren? And what does 2 to 5 mean? Kind of. So we're looking at the true what between Brian and Darren. The true what. Look at the minus right here, and we're looking at the true what between how many free throws Brian would make and we have the true amount of free throws Darren makes, the true amount of free throws Brian makes, and we're trying to estimate the what between those. So we're trying to estimate the true what between the free throws Brian would make on average and Darren would make on average. So we're trying to estimate the what. The true what. The true difference. The true difference. So if Brian makes 20 free throws and Darren makes 20 free throws, who would you expect to be better? So would you expect Brian to be better or Darren to be better, and why with this interval? With this interval right here, would you expect Brian to be better or Darren to be better at making free throws? And why? So this interval is estimating the true difference. We estimate the true difference between Brian and Darren to be between 2 to 5 points. When done, Darren minus Brian. So Darren's truth minus Brian's truth is somewhere in the interval 2 to 5. The true difference between Darren and Brian is somewhere between 2 to 5. No. Well, be careful. 100 points right there. There is a difference because 0 is not in the interval right here. So I think the true difference is somewhere between 2 to 5 points. And why would we know one of us is better? The way the mathematics is done right here, which one of us would be considered to be better with this interval? Like, there's evidence right here that one of us is better. And why? Just think of the way we're doing it with Darren minus Brian. So if the interval here is positive, which it is, this interval here is positive. So I think the true difference between Darren and Brian, if we were to look at them over the long run, is that someone would make between 2 to 5 points more in a game. So someone would make between 2 to 5 points more, and who would that person be and why? So I think the true difference between Darren minus Brian, like if I say Darren's truth for how many free throws he'll make and Brian's truth for how many free throws he'll make, that difference between the two of them is somewhere between this and this. That difference is somewhere between this and this. And why? So who would be better, Darren or Brian? I can determine. Yes, we can. The interval is completely positive. So the interval here is completely positive. And so which one of us is better, Darren or Brian? Well, so the interval here is completely positive. So which one of these do you think is higher probably? Like there's good evidence right now that one of these is higher because we're saying, let's take this number and subtract it from this number. And the interval we're getting is positive. Jacob, great job right there. Darren is estimated to be higher because the interval is positive. Remember, we're just going to plug in some fake numbers here just to show that if Darren's truth were to be something like 17 free throws and Brian's truth were to be something like Brian makes on average 14.5, what would be the difference between these numbers right here? If Darren were to make on average, actually needs to be 13.5 to make the interval work out perfectly. If Darren were to make on average 17 and Brian were to make 13.5, I'm going to change it, Jacob, so that the center of this interval would be 3.5. That would be at the center. And that's the sample difference we're seeing. But what if this interval were to go the following way? What if this interval right here, when we estimate the difference between Darren and Brian, because we go out and play basketball, and we estimate the difference between Darren and Brian to be something like this. We estimate it to be between -2 to 5. So it's somewhere, the true difference between Darren and Brian is somewhere between -2 to 5. So it could be that Brian makes on average this much more, and think of where the negative is associated with. So it could be on average Brian makes this much more, or it could be on average, now it could be that Brian makes this many more free throws on average, or it could be Darren makes this many free throws more on average. If the interval goes negative, it could go Brian's way because he's on the negative side. He's the minus side. So it could be that on average, Brian makes this many more, or it could be on average, Darren makes this many more. Brian could be better now. It's possible that Brian could be better, right? It's possible that Brian could make on average what now? Like the truth might be, it's possible that Brian makes on average this many more free throws than Darren when we take 23 free throws. It's possible, like up to this. So this is the true difference, right? So this whole interval right here doesn't go with mu1 or mu2. It goes with the whole interval. Like we're trying to estimate the true difference between this. So we're just coming up with an interval here to estimate the truth. Does that make sense, Tiffany? It doesn't go with mu1 or mu2. This whole thing right here, this interval is about the true difference between the means. So we're trying to estimate the true difference between the means. And it's possible now that Brian might make on average 2 more free throws than Darren. But it could be that Darren what? It could be that Darren makes what? On average 5 more free throws than Brian. But what do you see is in this interval right now? What is somewhere in the center of this interval somewhere here? Not at the very center, but what value is contained in this interval? Because a possible difference between Brian and Darren is what right now? What is a possible difference between Brian and Darren, which would mean there is no difference? So a possible difference between Brian and Darren could be what? 0. Does that make sense? Like, it's possible because the interval goes through 0 that there is no difference. But when we look at this right here, if we had an interval for Brian and Darren, and the interval were to be something like -2 to -6, what do you notice about this interval when we try to estimate the truth between Darren's free throws and Brian's free throws? This interval right here to estimate the true difference between Brian and Darren, like, what is really the difference between Brian and Darren? We're asking that, like, when Brian makes free throws, 20 free throws, and Darren makes 20 free throws, what is the real difference between them? And this interval right here, yep, we'll be doing that in a second, Tiffany, you got it. What do you notice about this? It's right there. Lunch made. Brian is, well, not probably. We have good evidence at this point. So we have good evidence at this point. Does that make sense? Why do we have good evidence that this Brian is better right here? Why do we have good evidence with this interval that Brian is better? So why do we have good evidence with this interval right here that Brian is probably better? Why would this interval right here be good evidence that Brian is probably better? It's exactly it, Jacob. So why would we have good evidence? You're right, Brian is probably better. We have good evidence of that. And why would we have evidence right here? Because we're trying to estimate the difference right here between these. So why would we have good evidence right here? Because the difference is negative, exactly. And so here, let's look at a jump version of this to make sure we understand. Because the biggest thing is we want to understand, like, what does this output mean? And what are we talking about? So let's go here and run a 2-sample t-test. Exactly. And so we're going to take a difference between, let's go people who are in Greek life and not in Greek life. And let's go high school GPA, and let's look at this. And let's see, is there a difference between these two groups? Now tell me, if you see right here this difference, so take a look at this difference right here. This difference is positive. So which of these groups had the higher GPA? The people who are in Greek life or the people who are not in Greek life? So wait, this is the difference we see between the yes group here and the no group. And then we have an interval to estimate the difference. So the way this is done right here, and it's very important to know how to read this output, like kind of one of those teaching us to the test moments. We need to know how to do the test, not just an assignment. So we're going to make sure we see the test right here. We're trying to estimate the true difference between those who are in Greek life and those who are not in Greek life. And the difference we observe is what? And that is correct. The people who are in Greek life, because the difference is positive, and you can think of it that this is the positive one and this is the negative one. So if you see a positive difference right here, on average, people who are in Greek life had this much higher of a GPA. Does that make sense? And then the interval here is completely what? When you look at this interval here is completely positive. So this interval would go from 0.0037 to 0.1177. And what do you notice about this interval? Great job, Jacob. Thanks so much for all the help right there. And what do you notice about this interval, which indicates to us that there is a difference between these two groups? What do you notice about this interval to estimate the true difference between the yes people in Greek life and the no people in Greek life and their GPAs? Now, it's a very small difference, but what do you notice is not in this interval right here? This interval right there to estimate the true difference between the GPAs of people in Greek life and not in Greek life, which is positive, does not contain what? So we think there is a difference. It does not contain what? Because we're trying to say, what is the real difference between people who are in Greek life and not in Greek life? So it does not contain 0. And it doesn't go negative, right? Because it's completely positive. So this means we think people who are in Greek life, that their GPA might be somewhere between 0.0037 higher to about 0.1177 higher. Maybe Tiffany, I'm not, but does this one make sense right here? Does seeing this output make sense right here that we think the difference between people's GPAs who are in Greek life, yes, and who are in Greek life, no. And the reason I'm able to write it this way is because of this output right here. So the reason I'm writing it that way is because it says right there, yes minus no, that's the order of it. And I think the true difference between people who are in Greek life and who are not in Greek life is somewhere between Greek life having 0.0037 to 0.1177 higher GPA. So this interval is estimating the true difference between those two groups. Yeah. Oh, definitely, Anna. We'll be doing that here next, I believe. Thank you, Anna, so much. And so does this make sense here that we're trying to estimate the true difference between these two groups? What is the yes? So the yes number would actually be, we actually need to go get that. It's not currently on this screen. To get the yes number, we'd have to actually go to Analyze Distribution. We'd have to go to Greek Life and do this by Greek Life, do high school GPA, and do stack. And the yes number would be, so the mean for yes, at least the sample mean, the observed sample mean, which is what we would use for our evidence of this. So y bar yes minus y bar no, because this is how we run the test. The y bar yes group is going to be 3.847 minus, there's the no up there, 3.787. And can anyone subtract those numbers? What will you get if you subtract those numbers? Subtracting those numbers would get you what? If you subtract those two numbers right there, what will that mathematically solve out to? That'll solve out to equals 0.06, and there's extra decimals we didn't carry. But that right there is the difference between the whats. This right here is the what. Like this that we're calculating right there is the difference between the two whats. So we don't know the truth right now. We make statements about the truth, but this difference is between the two whats. Like this observed difference that we see is between the two what means. And we just went and calculated it right there to get an estimate of the truth. And so that difference right there is between the two what means. We don't know the truth, though. We have to, in our null hypothesis, we make a statement about the truth that we believe that the true difference between the two means is equal to 0. And then we would have an alternative. But I do make it easier problem. I see exactly. So with this right here, this is the true difference. This right here is the difference between what? The yes and the no, and this is the sample means up here. Great work, great work. These are the sample means, and this is a statement about the truth with the null right here. So when we look at our problem right here, and so there's lots of different ways this problem can go, and that's why I want to make sure if you get to the test, it's not always the same way. What do you notice about we estimate the true difference to be completely what between these two means? Now, positive, negative, or we don't know. I'm only getting, oh yeah, no, I carried extra decimals. Sorry about that. The extra decimals are, if I wrote the numbers, great work there, Jacob. We estimate the difference to be between these true means, the true difference, we estimate it to be completely what? Completely positive, which means we would think which of these is larger. If the difference here is truly positive, and we subtract them this way, which of these would be higher? So if the difference here is completely positive, like when we subtract meat minus beef, and the difference is positive, that would mean the first number is larger. Like we would say there's good evidence at this point because the interval is completely positive, and Jacob, you see it right there, that this one would be meat for us. Because think of 10, once again, think of it this way. Just subtract two numbers right here, and if you do 10 minus 6, just theoretically, that would give a positive number, which would mean the first one had to be bigger. Does that make sense right there? Like, if we get a positive number here, then the first mean has to be the bigger mean because we're doing big number minus small number equals positive numbers. And we have good evidence at this point that it is a significant difference because the interval does not contain what? And here's a key thing we must know. Why do we think there is a difference right here? We think there is a difference because the interval does not contain this. And this is an important thing to see for your interval estimating the difference. I think there is a difference because the interval does not contain what? We'll do both of those. Casey, we can do that after the 320 next. So the interval does not contain what right here? So we think there is a difference because this is not in the interval. Review again. Since this is not in the interval, we think there is a difference. So what value is not in that interval? I've been on top chat this whole time. Wait, I need you to solve it, Tiffany. You got it. There is a difference because the difference does not contain 0. Exactly. So we believe there is a difference right here. So we think that meat is probably higher. The mean content for the meat hot dogs is probably higher because our interval is positive. So make sure to review those examples again. Look and think, what does your interval mean if it goes negative to positive? is completely negative or is completely positive, and it's really good review for the test. What does the fact that the confidence interval does not contain 0 mean? So ours does not contain 0, which means we think there is a what here? If we see that it does not contain 0, 0 would mean that there is no this, but ours does not contain 0, so we think there is a this. So this applies to maybe your interval in a different way, because if your interval contains 0, Jacob's right. Great work, Jacob. So if your interval contains 0, there's probably no difference. But our interval here does not contain 0, so we would say that there is a difference. When we say this right here, the difference in the two sample means is significant. Excellent work. And the last one, it's a good one to know. We'll be covering this more next time. With this last one right here, we have, I think we have one more 201 after this. Next, where'd my pen go? With this right here, great job, Timothy. Thank you so much. 100 points right there. If we make an 89% confidence interval, then what would the alpha level be? The alpha level is the outside of a confidence interval. Like if we do a confidence interval, the alpha level is the remaining portion on the outside. So what would the remaining alpha level be? What would the remaining alpha level be for this? Who knows what the remaining alpha level would be for this? 11% exactly. Great job, Tiffany. Another 100 points. Keep it up. So the alpha level is just 1 minus the confidence level. Do remember this is on a two-tailed test. So it's going to be 0.1 right there. And that would be the remaining, or 11%. It does want it as a percent, but I usually write it as a decimal. And that's got to, oh, check answer. There we go. Sometimes I think I'm doing like an actual quiz. Awesome work there, everybody. Let's head back. We're doing another problem right here. Great job. Amazing work. Thank you, Jacob. So much positivity. Jacob, thank you so much. The biggest thing is knowing the concepts. Knowing the concepts is really the best way to solve these, because then when you get to the test, you don't want to think of each my Pearson problem as like if I just solve this, then I never need to know it again. That's one of my greatest fears is being able to do each problem and being able to work it and understand it and the theories behind it. I think we did that one right there. We'll do more here in a second. We have the beef versus the meat. And then I think someone else mentioned another one. I know 320 asked one. 320 was asking about 1C. I thought there was another 201. Where'd the 320 go? 1C on 320. Which problem, Tiffany, can you put in the chat? We'll do that one next. Or we have two more questions lined up. We have the project, and then we have 320 in the project. And drop the question in the chat. And we'll take a look right here. 320 coming up here in 1 second. 320, 1C. Assignment 9. Oh, due tonight? Let's go take a look at some 1C right here. And we're getting R loaded up in the background. Let's take a look. Take a look. So I think Jacob was offering some really good help right there. Take a look at Jacob's advice. So make sure to go through and step through it. But check it out. And so the biggest thing is know how to solve them. We want to get to where if we see a different version of it, we know those answers. So we don't want to just know one version. We want to be okay, if I see it this way, it means this, and not just knowing memorizing oh, I saw it this way, it means this, but understanding what the interval means. So the biggest thing is know what the interval means. It's trying to interpret to you what the difference is, and it's trying to estimate that difference. So that's gonna be the biggest thing right there. We have covered the visualization, but we could, Jacob, if you want, that could be, we could do that. That definitely could be done. You bet. We have 2 things lined up, but Jacob, we can definitely do that. So what would it mean if it has a negative number, Tiffany? If it goes from negative to positive, what is it telling you that if the numbers are possibly a negative difference or possibly a positive difference with 0 contained in the interval, what does that mean to us? It's trying to estimate the difference, and we're saying, well, the difference might be negative, the difference might be positive, and then what is in the interval if it goes from negative to positive? What would be in the middle of the interval saying to you, well, maybe the difference is this? I don't know. We're trying to figure out, got these meat hot dogs, these beef hot dogs. What's the difference in their fat content? What is the true difference? Here we go, some 320. Let's check it out. 321C. 321C. Let's go check out 321C. Let's see. So would it be the mean fat content for each type of the hot dogs? Would it be, that sounds, I'm not so certain. That doesn't sound 100% to me. Oh, no worries, no worries. Here, let's go check it out. Let us compare the average demand for rainy days and non-rainy days after accounting for temperature. So we need to fit our model here. Let's go ahead here and fit the model. We need the library reg class. And let's go to data, ex4 bike, loading up the data. And we need to take a model and make it for predicting the demand. And the demand will be predicted from effective temperature and weather. I think those are the two. And then, so this format right here is very important to know for every one of the functions we write right here. We have y tilde x comma data equals. So the y variable is what we are predicting. The x variables are the explanatory variables. And you see here the formula y tilde x1 x2 comma data equals data. So it's y tilde x comma data equals, where we have multiple x variables right here, and you can see the y's and the x variables. Weather not found. I might have capitalized weather right there. Do we not have ex4 bike loaded up? We do have ex4 bike loaded up. Let me take a look. Demand y tilde x comma data equals. It says weather is not found. Does weather have a lowercase? Let's go look at the ex4 bike data set. And where was the typo? Oh, is it EX7 bike? I think it's EX7 bike. I think there's an EX7 bike, and we're using the EX7 bike. And I think the EX7 bike has weather. So there we go. That would be correct right there, Tiffany. We cannot determine it. Yep. Thank you so much, Jacob, right there. We would not be able to determine because zero's in the interval. Oh, EX5? Oh my gosh, EX5 bike. How many bike data sets are there? They're just sectioned off differently. It's all the same data, but kind of constructed differently, like with different variables, so we can look at different things and analyze different sorts of stuff. Anna, thank you so much. Now 100 points in the chat. So we have EX5 bike data right here, and we can visualize the model now. So let's go ahead and visualize that model. With the visualization of the model, let's go ahead and visualize it. We're going to visualize the model. And what do you notice right here? You're awesome. Thank you, Tiffany, right there. Good practice. So what do you notice right here about the no rainy days? When it doesn't rain, the demand would be what? Like, what do you see right here for the demand for the not rainy days? Let's just think about this. Like, what do we notice here about the demand for the not rainy days? The days where it doesn't rain, what do you notice about the demand? So here's a day, just some sort of day where it doesn't rain. Here's what we would predict. And we saw this in 201 for a moment. This is actually pretty interesting right here because you're noticing two lines. A line predicting when it doesn't rain, and a line predicting when it does rain. So what do we notice right here? What do you notice? That the days where it does not rain, what? The days where it does not rain, you would expect what? Just imagine you're communicating this to someone. You say, well, when it doesn't rain, I'd expect, and these are bikes that we are renting out. This is a major city right here. I think it's DC, actually. So we're renting out bikes, and you'd expect the demand to be what when it doesn't rain? When it doesn't rain, the demand for bikes to be higher. Exactly, we would expect. And this is how we talk about, in statistics. I'd expect the demand to be higher, but tell me this. How much higher? Like on average, or between 2 days that are otherwise identical, where one day it rains and one day it doesn't rain, I'd expect the difference to be what? What would you expect that difference to be? What would you expect this difference to be? So the difference you would expect to be what? And Tiffany, the difference could be zero. Does the difference of zero sound significant or insignificant? So for Tiffany's question, the difference could be zero. If zero is in your interval, when maybe there's no difference. And does that sound significant or insignificant if we say maybe there's no difference between the means? Because the difference could be zero if zero is in the interval. That's a possible difference. So what is the distance between these? Do you see that, Anna, right here? What is the distance between these two right here? Like the distance between these, and actually if you trace it down further, they would hit at the intercepts with a difference of this. Like if you went down here and you looked at their intercepts, the intercepts would, because the lines are parallel right now, these lines would have a difference at the intercepts of this value. So what would their difference be at the intercepts? That is correct. Excellent work, Tiffany. Excellent work. So what would what is that blue difference right there, Anna? Like mathematically, can you find that for me? The difference between a day where it does close. That is the intercept of the reference level. So the black line actually hits over here at 1,912. That's where the black line hits, somewhere about there. But the pink line hits how much below that? Where does the pink line hit? The pink line is going to hit where? The pink line would hit the intercept how much lower? And you can kind of see it. Think about this. Like, look at this. This goes from 2,000 right here to about maybe 2,600. I mean, that's not quite it. But the pink line is how much lower. It's important to like see this in the output. So that number is where the black line hits. And the pink line would be how much lower? Not the RMSE. And good answers, Anna. Don't worry. And great guesses. Just don't worry. This is the place where we practice. The pink line is actually that much lower right there. So that is the estimate of the difference when it rains. So when it rains, we'd expect the demand to be this much lower. So this right here is the blue coloring I've done right here is the mathematical difference. That's what I want to see. That's the difference. And so could you tell me where the pink intercept is at? Well, think about this. The intercept for the pink line is going to be 656 lower than the intercept, which is 1,912 for the black line. But they both have the same what? They both have the same what? Look at these lines. They both have the same what? They have different intercepts, but they both have the same what? They both have the same what, which is this. So they have different intercepts down there, but they both have the same that variable, which is the what. They have different intercepts. The pink intercept's lower, and Jacob, you got it right there. Great job. Which effective average temperature is the slope, because that's the slope coefficient right there. Effective average temperature is behind me as the x variable. So if you notice right blocking right there, that's the x variable. And so they both have the same slope. So both of you are correct right there. Effective average temperature has the same coefficient, which is the slope coefficient. So these lines are parallel, but they have different intercepts. So to go to also some other questions in this, is this difference you observe right here statistically significant? So this is good. This goes to Tiffany's question. Is this p-value right here one which we would reject the null for? Because this p-value is 0.0000366. So that's the p-value you see right there outside of scientific notation. So would we reject the null for this one or fail to reject the null? Like, is the difference right here, I'm talking about this difference right here, and this is the p-value for this difference. Is this difference right here statistically significant? That one is statistically significant, and Tiffany's would not be statistically significant. And we usually use an alpha by default of 0.05. Saying that something is statistically significant means that the p-value is below alpha, and that one is way below alpha. Super statistically significant. So we think about what we're saying right here. The difference between a day where it rains and not rains, like a day where it rains versus a day where it doesn't rain, the differences we see in bike demand is not due to random chance. Like, there really is a difference. I know this sounds like a no-brainer. Like, if you are renting bikes and you have a day where it rains, you would expect the demand to be lower, and the demand difference is not by random chance. Like, we're saying we see a very significant difference in demand. And this actually goes to what we're talking about today with practical significance. If you see about 656 bikes lower, and it looks like you usually sell about 3,000 something bikes or rent about 3,000 to 4,000 bikes, maybe like more 4,000 bikes, and your bike demand drops by 600 on a rainy day, do you think that's significant to your business? Do you think this drop from a day where it doesn't rain to a day where it does rain, and we see right here, usually you do about 4,000-ish bikes, and then when it rains, your demand probably drops. We would predict it to drop, not that it will. We'd predict it to drop by 656. That's practical significance. So that's like the effect. Think about the effect of rain. We talked about effect size today in class. The effect of rain is that we estimate it lowers your demand of bikes by about 656 bikes. So I'd say that is a significant impact to your business. You're like, dang it, it's a raining week. We're not going to make as much money because it's a significant impact on your business. And I guess the last thing to mention here, so here's a freebie, Anna. When we interpret this difference right here, so freebie right here. So thank you, everyone. And great practice, Jacob. Are you 201, Jacob? Jacob, excellent work. 100 points right there. I think Jacob is 201, following along and practicing some BAS 320 right here, doing indicator regression. You are? Well, great work. And thank you for all the help with the last questions and everything. excellent, excellent work practicing. And this is something you don't have to know, but it's the same sort of regression we were doing in 201, but we're now using categorical variables as indicators. So here's how we would interpret the coefficient of this value right here. This value being interpreted would be 2 days that are otherwise identical. Think about this. They have the same effective temperature. So they're otherwise identical. Like the effective temperature is the same, where one day it rains, which is what we're saying right here, and the other day it does not rain. We expect on the rainy day for bike demand to be lower by 656.097. Does that, as like a business person, make sense to you? Like, does that business make sense? There's one quiz drop for your exam. Yep. So if you've got all of them done except for 19, you got those hundreds in the book. So with this right here, does this make sense? 2 days that are otherwise identical, like they have the same temperature, like tomorrow it's going to be an effective temperature of 15 Celsius. This is in Celsius. And then Wednesday it's going to be 15 Celsius, but on Wednesday it's going to rain. So Tuesday and Wednesday have the same effective temperature, but on Wednesday it's going to rain. So on Wednesday when it rains, we actually expect, everything else the same on Wednesday. We expect the bike demand to be about 656 lower. 2 days that are otherwise identical, but on one day it rains and on the other day it doesn't rain. The bike demand for the rainy day is expected to be 656 lower. And that is the interpretation of indicator variables where we compare it to the reference. And hopefully this visualization here makes sense. So Anna, great work on this. I think we're going to do some, and Jacob, if you want, we can do some visualization. It's due tonight. So Jacob, do you want to do visualization after this? Because we only got one more thing lined up. I think the next question was Project 2 stuff. So Jacob, your call, and huge props to you. Big help, and thank you so much. We'll clear the screen right here. You're welcome, Anna. We say holding effective temperature constant? Yeah, William, great start there. Kind of combined your name to Wilson. But could we say holding effective temperature constant instead of 2 identical days? Yep. You could say holding. So you could say 2 days where effective temperature is held constant between them, but differ. But one day it rains and the other day it doesn't rain. The biggest thing on William, William, thank you so much. Just saying that they're virtually identical, like which is hard to think of, but mathematically that's what we're doing. Because sometimes it's like if you have a ton of variables, can you say 2 things are otherwise identical? Like they have the same blah 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 blah, but they only differ in this by 1. So then it becomes like we're solving math equations, which might not apply. It's pretty interesting. Like when you get into like a huge multiple regression equation, two individuals who are otherwise identical have the same weight, the same height, the same age, the same year they went to school, the same everything, but one of them eats one more taco a night than the other one. The person who eats one more taco is expected to have this much more body fat than the other. So if no one has a question, I'd like to know. Yeah, we'll do making the graphs next. We've got the project thing. Let me go look at the project. And you bet, Jacob, right there. I don't mind covering things twice, and especially doing so much huge help. And I love it when people are like answering the questions, asking the questions. Let's go back here to the main screen. Excellent work. Awesome times. Great job, everybody. So in Project 2, we were talking about the mean or proportion. Let's do a little bit on Project 2. Let's talk some Project 2 for Stat 201. So let me go grab that up. And excellent work, everybody. Great work, Tiffany. Great work, Anna. Great work, William. Jacob, excellent work. And we're going to grab some Project 2, and then we're going to do some visualization. But put those questions in the chat, because after that, we still have time. So right here. Class doesn't start till a while. Brad Mondo sends me so many alerts. Got a coupon. I might buy some Brad Mondo products. I buy them for my fiance. Shout outs to Brad Mondo. Stat 2 approved. There, go to the project. Where is that project? It's showing the syllabus. Oh my gosh. Project 2. Let's go check it out. Here we go. Project 2, Stat 201. The biggest advice I can give you is do the project early. Do the project early. So let's go here to the Stat 201 page, open it up, and we can see right here the instructions. We have it here so we can update it. You might say, well, wait, why are you sending me like to 10 different pages? This is if we want to update it, and it has all the instructions. So the executive summary, make sure to cover all parts of it, like who are you writing this report for? And you're going to choose the company you're working for. You're going to choose the data you've been working for, and you've been working for this company a while. So this is a company that you've been working at for 5 years. You're going to analyze the data here and give them your results. And you're kind of just talking to people you know. Now, be professional, but you're going to try to write it in a way that they would understand. So the biggest thing is the executive summary at the start right here is going to cover everything. You should have 3 key tasks. Orient the reader to what you're talking about. Hey, we work at this company and here's our goals. Don't start with hey. I will get to that in a second here, Tiffany. Great question. And so we have right here, the company you work for is going to be dependent. So I'm not going to use any of the data sets we're using. I'm going to use a different one here. But you're going to pick a data set and then you're going to talk about what company you work for. So you're going to come up with that company yourself. Whatever company you want it to be, you pick it. Boom, that's your company you're working for. You need to make sure people know what your company is. You're going to talk to people, this is our company. We work for Stat 201 Incorporated. Everyone's going to write that right now. Don't write that. Don't choose that. I don't, because we do check for plagiarism, so don't pick Stat 201 Incorporated. And then you are going to talk about the data set and your goals with this. Talk about your key findings in the data. Now, don't write your executive summary first. You need to first get your key findings from the remainder of the report. Last but not least, you need to make sure you give the decision you're going to make after you collected the data. So 1, orient the reader to who's your company, what's going on with it. 2, make sure to give your key findings, what you found throughout the report, with numeric backing. So with numeric backing, I cannot highlight this enough. Give the numeric backing, please, 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 please. Where'd that numeric backing going? So give the numeric backing of what you found. And last but not least, give what you're going to do because of all this. Tell it oh, now we're going to change this. We're going to do this. Here's where our updates because of this. Be very direct. You've been working for this company for 5 years. You got a little bit of leeway to say we should really be doing this. But give your numeric backing to say, in the result for this, we found this, and this really believes me that we should do this. Here's my other key findings, and walk through. We have here a 1 sample Z, and you'll do a few things right here with making the graph, going through the successes, create a confidence interval, interpret the interval, all this good stuff. Other stuff right here with a hypothesis test. You'll do the 1 sample t-test right here. All this excellent stuff. The 2 sample t-test, the future research, and the neatness. Now, there's a lot of moving components to this, but I want to point something out. The number one way to know you're doing this properly is to look at the what. Someone say it in the chat. What is the number one way to know you've done this properly? Are we not doing partial credit? Might ask if we can update this. The rubric. There's some partial credit. Finally, some partial credit right here. Might be asking if we can put a little more partial credit on this. So compare the difference in demand. What? Is this the right rubric? Oh, that's Simon 9. Oh my gosh. This is the... I was like, compare the difference in demand. I was like, that doesn't look right. Hey, there we go. Here's a rubric we want to see. I was like, something looks a little bit off right there. So here is the rubric. And I was like, why is there not much partial credit? So if you look at the executive summary, remember those 3 key things I told you to talk about? Outlines what is being researched. Summarizes important results. Look at these things right here. Full marks. It is clear from the start who the project is for and what is being analyzed. Full marks. A summary of results found through the project is given. The goal is shriek. The goal is what? I must have wrote that into a paragraph. Oh, shrink. The goal is to shrink what is written in the report into a paragraph that communicates important findings. Must use numeric backings. The goal is shrunk. Let's change that while we can. And so the goal is shrunk. We're going to shrink it. The goal is shrunk. That's grammar, right? You're going to shrink it down into a paragraph. Here you go. Executive summary action items. Can you go over how to do? Yeah, we'll do that soon here, Gracie. Great question. We'll be doing that soon. Jacob, we're going to do some visualizations and do that here, I think, next. Yep, great questions. And so the action item is clear and also connected to the report. Going here and doing the 1 sample Z, which is kind of a lot like you're doing. Creation of a bar or pie chart has numeric backing on display. So you'll create a bar or pie chart. Make a confidence interval. Do the 1 sample T. Then the 1 sample Z, then do the 1 sample T. But is it clear? I want to state this again and again. If you're going through your report, this is how the graders will grade you. So when you look over here, project is overall neat. Project doesn't have to be perfect. All of this right here. On the first project, I left a comment on the assignment through Canvas would be, yeah, email me and I'll handle it immediately. I can take a look, Jacob, and see if some points, like I have given a lot of points back. So I might definitely do that. It's quite possible. I might be like, yeah, that was graded way too harsh. One grader went a little bit too harsh in their grading. If anyone else is seeing this, please email me immediately. I don't always see the comments on the thing because it doesn't send me alert if someone puts comments. It doesn't say like this person added a comment to this. Future research examines new ideas that go beyond the report. So you're not just going to restate ideas right here. Future research is clear and also connected to the report. Like it needs to be connected. You can't say like, we work for Krispy Kreme and we want to go into education. Well, I mean, maybe your data supports that, but you need to somehow connect it to the report. It's going to go beyond the report, but you should be connecting this to the report somehow. But the best advice I can give anybody is while you're doing the project, make sure to be going through. Now, what's the deal with all these data sets right here? We've got 4 different data sets for you to pick from. So it's your choice what data to use. I won't be using any of this data right here. Like we've got the student data. Like I'm not going to use this data when I do examples because I don't want people, every time I open Jump, it says, open your license. And then I open the license and I've been trying to download the new Jump and it won't let me download it. So here we are with a data set right here. I think this is this a different student data set than one I've been using? It is a different student data set. Good. So I've got my student data set. You've got your student data set. But with this, you will open up any of these data sets right here. And there is a file talking about the different variables in here. We've got height, weight, desired weight, people's GPA, how many days they text. And so these are all different variables you can analyze right here. So you will use any of these data sets of your choosing and choose any of these variables of your choosing. So one of the first tasks you see on the project is to do, beyond writing the report and everything, one of the first tasks you see on the project is to do a what? Let's go over to it. I believe it is a 1 proportion. So the 1 proportion is the first thing we are doing. Let's go right here. 1 proportion or 1 sample Z. Pick a categorical variable with 2 levels. You are interested in make a bar or pie chart of a variable you choose. Make sure the bar or pie chart has numeric backing on the display. After making the graphic, explain the results. When explaining results, make sure to cite the numbers in the graphic. So this here is a task. Let's complete just this first task and see how it would be done. Once again, I'm using a data set you don't have. It's a different student data set, but I need to pick a what level categorical variable. Who can remind me? I need to pick a what level categorical variable. I can cheat if I look up here because I can see which ones apply. I need to pick a what level, just put a number in the chat. I need to pick a what level categorical variable. And then I need to make a bar or pie chart of it. I need to put the numeric backing on it, and then I need to explain it to the reader. So that is our first task right here. Here's our first task again. Pick a what level categorical variable, which means there's this many answers to the question. Levels are like the answers to the question. 2 level right there, Alexander. Great work. So we're picking a 2 level categorical variable, and we're going to make a bar or pie chart of it. Then we're going to kind of yes or no. It could be yes or no, or it could be things like this one here is female or male. That works. But notice here we have some that are 2 level, like a lot of yes, no's, which pretty much it could be answered yes, no. There are some multiple yes, no's though, but so gender would work right here. How about were you born in Tennessee? I'm going to use are you born in Tennessee? So you go to analyze distribution. Yeah, exactly. So we can't use an identifier. Exactly. So we can only use 2 level categorical variables like born in Tennessee. And we'll go ahead and click OK. And then we'll click the top right arrow and click stack. Now the red arrows are where your options are at. So I'm going to go to this red arrow and go to histogram options, count axis. And then I'm also going to go to histogram options and why not show counts? It doesn't hurt to do that. I'm going to stretch it out a little bit. I'm going to go here to histogram options. These are just extras. You can choose things you want. I'm going to go here to a nice little purple right there. There we go. It looks really pretty right there. So now, and I'm going to hit control click. I don't like that it's clicked. You can also go to rows, clear row states if something's selected. Clear row states. Where's clear row states? There it is. If you select something, one of the quickest ways for students to go here is to go to clear row states, and that'll clear the row states. So what do we have right here? We have we've completed 1 portion of the project right now. From this point, we just need to take a picture and talk about this. Well, think about this. From this graphic, I learned that in my sample of 806 students, there were 319 of them that were not born in Tennessee, which represents 39.58% of the students. There were 487 students who were born in Tennessee, which represents 60.422% of the students. Now, what do you notice I'm doing? I'm giving you all the numbers. I'm telling you this information, which is in the graphic. From my, analyzing the students, whether or not they were born in Tennessee, I find that 319 out of the 806 were not born in Tennessee, which represents 39.578% of students. We have also 487 students out of the 806 who were born in Tennessee, which represents 60.422% of the students. This is what we're talking about when we say give the numeric backing. And maybe you're analyzing this to figure out, I don't know, it's your company, so why do you care if students are born in Tennessee? I don't know, maybe you're trying to, I don't want to give any, I just fear if I say something, if you use a student data set, you might do the exact things I do. And I like the innovation. I like the ideas people come up with for their company. And so let's do one more part of this. The next question is, so that basically does everything here. We need to take a picture of that, put it in there. Next, identify which level of your variable you will consider a success. Create a confidence interval and choose any % confidence. Include a separate picture of the confidence interval. Interpret to the reader the confidence interval based on the level you choose. So who's got this right here? We're going to go to the red arrow and go to confidence interval. Now, pretty much, I make 95% confidence. I'm just saying. That's what I make. It's what we do classically in statistics. I'm going to choose the students who are born in Tennessee. So think of this. And I want you to consider this question. I am what % confident? 95% confident. The true proportion, because we're talking about are you born in Tennessee? I am 95% confident the true proportion of students born in Tennessee is contained in the interval 57% to 63.74%. I am 95% confident that the true proportion of students born in Tennessee is contained in the interval 57% to 63.7%. So we won't quite do the next one, but let me ask you this. Do you think 50%, and Jacob, this goes back to our first questions, do you think it could be true that 50% of students are born in Tennessee? Yes or no? This goes to exactly what we're doing right now. Do you think it's true that 50% of students are born in Tennessee? Do you think it's true that 50% of students are born in Tennessee? Yes or no? Yeah, I totally think that could be true. Do you think it's true that 50% of students are born in Tennessee? Do you think that could be true? Do you think it might be true? Or you say, no, I've got evidence against that. What would you think? Or anyone in the chat wants to say, do you think it could be true that 50% of students are born in Tennessee? Or, nah, I think I got evidence against that. And why might we have evidence against that? Do you think it's true? Well, it could be true, but I don't think it's true. And I'll tell you why I don't think it's true. This interval does not contain what? If you look at this interval right here, this interval, 57 to 63.7%, does not contain what? That interval, estimating what the truth might be, we're saying, well, maybe the truth is somewhere between 57 to 63.7%. It's probably between there. Probably, maybe 95% confident. I think the truth might be in there. It doesn't contain 50%. So if I go here, anything's possible, right? But we think it's unlikely that 50% is true. So if I go here to test probabilities, like kind of doing the last part of this, and if I go and test a probability of 50% for the yes, I think we're doing this for the last one. If I test a 50% probability, I'll see if this is the last thing we're doing. Guess what we would do to that null hypothesis? If we were to test the probability of yes being 50%, what would we do to the null of 50%? Think 50% is not in the interval. So if I were to test 50%, I would what the value of 50%. So I'm saying, let's test to see if it is 50%. Well, 50% is not in my interval. I would reject it. So we're testing if 50% is the truth. We're hypothesizing. Well, let's hypothesize 50% is the truth. I would reject that. What if I did a different test where I hypothesized 60% is the truth? If I were to hypothesize 60% is the truth, so we're going to go over here to a new test. Did it open it up? Oh, can I redo the test values? Oh, it's all the way over here. So now if I were to hypothesize 60% is the truth, guess what? Now with 60% as the truth, I would not reject it. If I hypothesize 60% is true, I would not reject it because that's kind of close. Like, yeah, maybe 60% is true. But 50%, we have good reason to reject. Also notice 60% is inside of the interval. Anything inside the interval, we would fail to reject. Exactly. And I think that might be like the remainder of this. Finally, include a value as a hypothesized value your company wants to test in a does not equals test. Explain the decision your company makes about the hypothesized value and how they arrived at this conclusion by using the confidence interval. So actually, you don't need to do this test right here. This test is not required because guess what you can do? To run a hypothesis test, all you would need to do is what? You don't need these tests because what is the only information you would actually need to run a test right here? All you would need to do is look at your what and see if the value is inside of it to say, yeah, that seems possible. So you can say like, I don't reject that because it's where. You could run a test just by looking at that and saying, oh, let me look at that and say, oh, well, that value's inside of there, so it's possible. Like, I think that could be the truth. Is it in the interval? Yeah. So we're saying, oh, it's inside of there. It's in the interval. So I think it could be true. And so because the value, exactly, Jacob and Alexander, if the value is in the interval, we would not reject it. So here, you ready? Watch this. You can solve this so quickly. Tell me, will the p-value be high or low for 0.59? If I test 0.59, will the p-value for 0.59 be high or low? I'm going to test 0.59. So when I test right here and I go to test probabilities and I test 0.59 for the yes, will the p-value be high or low? And just think, do you reject 0.59 or not reject? So will the p-value here be high or low? 0.59 is in the interval. Careful. Low p-value means reject the null. So if the p-value is low, we'd reject the null and we'd have evidence to say that 0.59 is not the truth. If the p-value is high, we don't reject, right? Then it's high. We do not reject it, so the p-value here would be high. And look, the p-value is high. We don't reject the null. So give me a value. Don't go crazy. You could if you want. But give me a value where the p-value would be low. Give me a value to test where the p-value would be low, which means you would reject that value. So give me a value that we could test for the true proportion of students being born in Tennessee that we would reject. You come up with it, correct? And you can just mention a value. Like, you don't actually have to run the test, but you could confirm it. So you're just understanding the connection between confidence intervals and tests. So yeah, which sounds like people are getting 70%. Ooh, that's really outside. Do you know what I can tell you what the p-value is going to be? Jacob, I'll throw you 500, or Alexander or Jacob, I'll throw you 500 points if you can tell me what the p-value is going to be on this test. So that's very far outside the interval. That's really outside the interval right here. This is way outside the interval. I can tell you numerically what the p-value is going to be. I can say, like, the p-value when it reports, it's going to be this. Jacob, you got it right there. That's totally right. It's going to be 0 because this is like super unlikely. Like 70% we reject, like, with a lot of evidence. Like, we really don't think 70% is true. It's very far away from my interval. If you see where 70% is at, like, I reject that. That is not true. Does that make sense here, Jacob and Alexander? Like, how we could use an interval to run the test. And then 49% we'd also reject. 0.49 we'd also reject and be like, I reject 0.49 as the truth. It's very far outside the interval. We have good reason to believe that 0.49 is not the truth. And if we run the statistical test, we'd get a p-value that'd be very, very small. So hopefully that's connecting the dots on how confidence intervals and tests are achieving the same goal. But great work there. Great work. Good practice. And that's the first question. Alexander, are you done with the first question? I think Alexander, the dots. It's my accent. Alexander, I think, is done with the first question, right? Alexander, you already have the first part of the project done right there with making the z-scores. Like 10, 15 minutes of just a little bit of jump work right there, making it. And yeah, I think that was it. Let's go here and look at the visualizations, making the graphics. So we're going to do making some graphics for the visualizations, and we'll do some conditions. People were wondering about those conditions for the graphics. Where'd it go? Conditions for the graphics. On our way. You got it, Alexander. You got it, man. Conditions for the graphics. Let's go take a look. The last visualization. No more visualizations after this. Cheer it on. No more visualizations after this. This is it. Visualization number 7, how to make the graphics. Let's go check it out. So we got the Stat 201 survey data right here. You need to take a sample of 223. This comes out of a full data set of 4,122. So that's definitely less than 10%. Hint, hint, hint. Definitely less than 10%. Every time Every time I open Jump, it says, where's your license? And I say, here's my license. It says, thank you for your license. And then it opens Jump. No idea. Maybe tonight I'll try to re-download the Jump 16, but it says crash on it. Like I tried to download it, it says fail download, fail to download. So when I'm back on campus, I'll download it and put it on a memory stick and be like, boop, put it on this computer. Okay, so for the first one right here, I hate how these variables look. It's because I have it so crazy big, sure. So with this right here, our first interval is going to be, I believe, a confidence interval for the true proportion, which we were just doing a second ago. This one's going to be a 99% confidence interval. You will use the variable arrested. Take a screenshot of the bar chart, the frequencies, and the confidence interval and put it into your Word document. So with this right here, let's go back to the data. I don't know what it asks for license. And you are going to do one for if students are arrested. Now, I'm not going to do that one right here. We need to take a random sample. Please take your random sample. Go to subset, put in 200 plus the last two of your UTID, and click OK. And now we have our random sample of 243. Make sure you see your random sample. Very important. You'll lose points if you don't have it. So now we're going to go to Analyze Distribution. Analyze Distribution analyzes one variable. Analyze Distribution analyzes one variable. And with this, we're going to analyze a categorical variable to find out an interval for the true proportion. Like, what is the true proportion of students who are in Greek life? Like, I don't know, students who are in Greek life or not in Greek life. I want to know, what is the truth for the amount of students in Greek life? Like, imagine if you went out and talked to 10 students and 6 of them were in Greek life, what would be your best guess of the proportion of students who are in Greek life? Now, this does fail the success failure condition, but if you were to talk to 10 students and 6 of them were in Greek life, you'd say, well, I guess about this percent are in Greek life. You'd have a very small sample. It would fail the conditions for making the interval, but you would guess about what percent. If you talk to 10 students and 6 of them are in Greek life, you'd say, well, my best guess is this is the percent of students who are in the interval. And that's all we're doing here. We're just talking to a bigger sample. We're talking to 243. 60%, 0.6. Great job, Jacob, right there. You got it. So we're doing the same thing here, except we're talking to 243 students. And there's my 243 students, and 72 of them are in Greek life. So you can see right here, just thinking about what the output shows you, from my sample of 243 students, this goes to the project a little bit, 72 of them were in Greek life, which is 29.6%, and 171 were not in Greek life, which is 70.37%. But this is what we saw in our sample, but now maybe the truth is somewhere around there. We would want to know a confidence interval for the truth to estimate what the truth might be, and I think I can zoom in on this. There we go. So this is how we make a confidence interval if you want to make one that's not 90, 95, or 99. Those are just the classic ones. And you can put in any value like 0.999. There we go. So now I am 99.9% confident that the true proportion of students who are in Greek life is contained in the interval 21.02% to 39.96%. So if I were to talk to someone, I'd say, I'm very confident, 99.9% confident, that the true proportion of students who are in Greek life at UT is somewhere between 21% to 40%. I'd probably round it. But if you're writing in a report, you might just write the decimals. But does this make sense here, Jacob? We're trying to think of like, what is the actual proportion of students who are in Greek life at UT? Well, it's probably somewhere between 21% of students are in Greek life to 40% of students are in Greek life via our estimates, via our sample, and creating an interval to estimate what the truth might be. We saw about 30% in our sample, so the interval has a margin of error of about 9% right here. So 30% plus, or 30% plus or minus close to 9%. This uses, I think, chi-squared ways of doing it, so it's not always perfectly symmetric on the interval. It does a little bit better of approximation. So one thing you might want to look at, though, for your interval is I passed the success-failure condition here. I have at least 10 successes and at least 10 failures. I'm just putting this flat out there. Yours might not have at least 10 successes and at least 10 failures. You have what you need. Awesome, Jacob. And so for the next graphic right here, which there was also a question about the nearly normal, now we're going to do a quantitative. So once again, using your random sample, we have right here, no, that's project. So now we're going to do it for the mean, which is also very similar to the project. You're analyzing Q15, and you're going to do analyze distribution. Again, Jacob might have figured out the second part right here. Analyze distribution, and you're going to pick a quantity. Well, you're going to use Q15. That's the one you're going to use. I'm going to use a different one. And let me go to pet expense. And so when we get to pet expense right here, you'll see it's actually very skewed, very skewed. With it being very skewed, would I pass the nearly normal, yes or no? Now be careful. Be careful, because there's a trick to the nearly normal that people forget. The nearly normal has 4 steps to it, and the fourth one's kind of like a saving step, which pretty much, maybe we should just go to the last one, because it pretty much saves you every time. The first step is to look at the histogram. Doesn't look normal. The second step, which you don't need all these, is to look at the normal quantile plot, which is a normal probability plot, and ooh, that doesn't follow the straight line. Ooh, see that there? That doesn't follow the straight line. So that's a problem. The third step is to do a goodness of fit test, and the goodness of fit test tells you if the normal curve is a good fit. And over here, we see that we reject the null, low p-value. There it is, low p-value, reject the null via 2 different ways of doing the test, Anderson-Darling or Shapiro-Wilk test, and we both reject the null, saying that the normal doesn't fit. But wait, there's more. There's a way to pass this. I'll go back to it here in a second, Jay, but you got it. I'll review that at the end again. This is the third condition for quantitative, and we actually pass the condition. You might say, how in the world do we pass it? Well, the reason being is the central limit theorem. Although the distribution of singular observations might be very skewed, the distribution of the mean, theorem applet, the distribution of the mean for a sample size of 250 is going to be normal, because we might have a very, very skewed distribution, or we could even make it more skewed. And this is only using a sample size of 25. But if we do the sample distribution of the sample size for us on the mean of the first input, I can show that. Gracie, good question. I'll go back and show that again. I'll show why we can kind of use what I showed, and exactly, Gracie, good question. And so this is the third condition on quantitative distributions right here. We would pass, and why do we pass right here? Because to pass the nearly normal, we can say that our sample size is large enough such that even if we have a skewed distribution, the distribution of the mean for a sample size of 243, even if we have a very skewed distribution, with a large enough sample size, the distribution of the mean, which is what we're analyzing, not singular observations, the distribution of the mean will be nearly normal. And this is the way to pass via the large enough n. And we have a confidence interval here. I'm going to go back and do the condition for the other one, because thank you so much for all those questions. And we do have this in other videos too. Like, if people are wondering, like, can you interpret this part more? Just hop into the questions and ask. But we want to make a 92.5% confidence interval. Make sure to use your data. I'm using a different one. You will not be doing pet expense, but I am 92.5% confident the true mean of pet expense is contained in the interval $443.48 to $635.34. Like, I'm 2.5% confident the true mean of pet expense. Going back to the other question about proportions, the Gracie brings up such a good point right here. The condition is NP hat and Q hat, but watch this. Here's the trick. The formula NP hat greater than or equal to 10 and Q hat greater than or equal to 10 is what we need to check, right? How do we get P hat? P hat is equal to X over N. So if you solve for X, what would X equal? Solving for X, X equals NP hat. That's what X is equal to. X is the number of successes in the sample, which is the sample size times the sample proportion. We'll see this here in a second as I solve it. But this value right here is both of these. That is both X and that is NP hat when you solve it. Because N is going to be 243, and then we would multiply that by 0.29630, and that will equal to, good question, this goes to a little bit of a theory on it, that both those values are equal. 243 times 0.29630, and if you carry enough decimals, it is 72. So this is 72. And then NQ hat, it will work out. We'll just write it right here. 171 would be equal to 243, which is N and then Q hat. Yeah, no, Gracie, thank you so much for asking about that. I've done it so many times that I just know that X is NP hat. So it is, when you solve it out mathematically, that P hat is X over N. So X is NP hat, like, because P hat is the sample proportion, but you could solve for X and X is NP hat. And so if you solved this right here, you would get that number. So this is NQ hat right here, and that's the value. and both of mine. So mine does pass. So this goes to Jacob's question. You want at least 10 on both of these. So Jacob, mine does pass because both of these are greater than or equal to 10. Make sure yours does, or comment if it doesn't. So mine, because maybe some people's won't pass. Just kind of putting that, hint out there. What questions are there? We still got a tiny bit of time. Throw those questions, and great work, everybody, working on these right here, making sure you see it, and also knowing the condition for the conf roles and p hat and q hat, because we only have p hat and q hat here. So just solving that out, showing this mathematically right here, and you can check it by looking at the number of successes. I was wondering if we have to go over the follower conditions on the nearly normal, or just use. Great question right there, Kaylee right there. Oh, is that Kaylee? I swear that I can't see what kind of dog that is. It looks like one of our dogs that we used to have. Like it looked like one of our old dogs, and then yeah, no, good stuff right there. Let me see right there. What kind of dog is that? Is it a beagle? Looks like a beagle. The conditions. Aw, it's a beagle. It is a beagle. I knew it. A beagle. Her name is Sky. Oh, Sky looks really nice right there. So if I'm to talk on this, here's how I would explain it. Great question, Kaylee, right there. I would say we pass the nearly normal condition because even though my distribution is heavily skewed with a sample size of 243, we have a large enough sample that the distribution of the mean will be nearly normal. So I'll repeat that again, Kaylee. Even though my distribution is heavily skewed, my sample size of 243 is large enough, keyword, that the distribution of the mean will be nearly normal. So we pass. Does that make sense? Read one more time. Even though my distribution here is heavily skewed, my sample size of 243 is large enough that the distribution of the mean will be nearly normal. So that should do it right there. That's a good enough way of doing it. If the data looked normal to begin with, we could just say the histogram looks normal, we're good. You might go into greater detail since it's graded, to be like, the histogram is normal, so the sample size here is way large enough, or it passes a normal probability plot, or it passes a goodness fit test. But this one right here, I'm going to use the large enough n way of passing. That's got it. Yeah. So make sure, 1, mention the shape of your distribution. 2, mention your sample size. And then 3, mention if your sample size is large enough that it's like going to pass the condition. But that's got it right there. Awesome stuff. Let's hop back to the main screen. Keep asking those questions. Just be like, hey, Brian, does this look good? Or what are we doing right here? Great work. Excellent practice, everybody. What other questions do we have? We have just a few more moments. I'm going to send out the reminder to class as you prepare some questions. Whoo! Man, I tell you, everything flies by. Tomorrow's Thursday, already Haslam Friday. I can't believe it. And then next week's like our last full major week of school. And then we're like going to be finishing off classes and everything. Oh my gosh. And then winter break, and then winter mini term. And then spring. I've got a big idea for spring. I'm debating it. I'm debating doing like a what was it? I'm debating doing like a AP statistics review. I wonder if it would help out. And then like trying to converge that to what we're doing, because I don't know, I just thought like maybe we could get some like more people watching the channel, like I don't know, some like more questions, like not during office hours. So I was thinking of doing like AP hour or something like that. Just an idea to be like, let's do AP hour class in 30 minutes. Big bonus. See you soon. Click here. There we go. I like teaching statistics, and whenever someone tells me they don't like statistics, it's all right. Like I don't feel really bad, but I've had multiple people tell me like, oh, I hate statistics, or I hated that class. That was no fun. And I'm like, but I like stats. Stats is fun. Can we do Canvas content number 9? Let's do it. Let's do Canvas content number 9, of course. So basically, I worry like a bunch of people are being taught stats. This is like Brian's great fear. And there's like, I hate stats. Like, I mean, don't worry if you hate stats. That's all right. But like, I hope it's not like your least favorite class ever. I hope you at some points are like, it's kind of cool what we can do. I see the point of it. To me, it's about data. It's about making decisions. And I just love it. I like data. I like data. All that good stuff. Oh, Kaylee, that means a lot to me. 100 points right there. And it's all right if people hate the class. Go describe how the randomization condition pass. Kaylee, great question. See, then you follow with my favorite class. But the randomization condition would be passed because we took a random sample. Like by virtue of taking you could literally say, By virtue of taking a random sample of the 4,122 students, I think that's the sample size, we have passed the randomization the random condition. So we have taken a random sample, thus we pass the random condition. So by virtue of doing it, you pass it. So very much clear on that one. And the 10% is also passed because the sample size of 200 something is less than 10% of the total population. Great questions, Kaylee. Keep it up. Here we go to the main screen. Okay, we're acing today. Man, yesterday my brain was fried. End of Office Hours yesterday. Don't watch it. Don't watch it. So here we are with some Canvas content number 9. A new diet is being tested. The inventor of the diet, I don't know you invent diets, sure, like Atkins and all that stuff, keto. The inventor claims people lose 10 pounds after 6 weeks. So they're saying, if you take this diet, on average, you will lose 10 pounds. They can't claim everyone will lose 10 pounds, but they're saying the average weight loss is 10 pounds. So the null has the equal sign. Yes! Look at that. The null has the equal sign. That is their original belief. Now you might say, don't I need evidence for that? Well, we are researchers, and we are concerned that this claim is exaggerated. So we'd want to show evidence that the true mean weight loss is what? And that's what mu stands for. Mu is like the true mean. Like if you were to analyze everybody and figure out how much weight people actually lose on this diet, that would be the true mean. Like for all people who are on this diet, which we probably don't have data of. Yeah, jump it, put it in here. No, throw the question in, Matthew. We're getting close to the end of office hours, but put the question in. I teach in 27 minutes, but do it. Less than what they claim, exactly, which is hypothesized. Great job, Jacob, right there. So we'd want to say the true mean weight loss is less than what they claim it to be. And drop that question in the chat, Matthew. We're going to do it. You got it. Your homework's due tonight, so let's do it. Next, we have a test. So we're going to run this test right here. We were talking about this today in office hours, during class, I mean. And when we run this test right here, we are going to run a t-test. How do I always hide my pen from myself? Oh, that's not good. Oh, here it is. Magic. D2, you got it. We'll do that here next. And so a new diet is being tested. The inventor claims 10 pounds. So that is mu naught. We just talked about that a second ago. That is their claim. And they're doing this with 25 people. That's their sample size. We're concerned it's exaggerated. The sample, which is the sample mean weight loss, with a standard deviation of 7.2. Now, I've made errors on this one by not writing down all my notation. If you don't write down the notation, you might make an error, and you might be like Brian, which is not good. And so here we go. And so Y bar is the sample mean of 3.4, which is way lower than 10, which is what they hypothesize. Next, we go here and take the standard deviation of 7.2, divide it by the square root of 25. And this is all going to solve for the t, which is the test statistic. It's on a distribution with n-1 degrees of freedom, but that is the test statistic we are solving for. So let's go ahead and go to the calculator right here. And this will help us solve right here. So we are going to go 25 square root, which is 5, and 7.2 divided by 5. And then we take the difference up top of 3.4 divided... Don't do that. 3.4 minus 10 divided by that. And the difference is negative. Make sure to put a negative. I think I've made an error on that before. But this is a negative difference because it is below what they claim. And that's really far away. That would be a p-value of basically 0. We're not going to solve for the p-value. We're just finding for the test statistic right here, which is the t for this, with n-1 degrees of freedom, which would be 24 degrees of freedom since there were 25 observations. So it says to 2 decimals, negative 4.58. The next question is a good thing we can memorize. And so help me out right here. Oh my gosh, what did I do? The next thing is going to be a type 1 or type 2 error. Now, there's no type 3 and type 4 error. A type 1 is when the null is true and we reject it. That's a T. A type 2, this is a 2 right here, is when the null is false. That's an F, and we fail to reject it. 2 Fs. So when we reject the null and the null is true, I see true right here, and we're only talking about the null. So remember when I said a type 1, just remember type 1, there's the 1, is when the null is true and we reject it. A type 2 is when the null is false and we fail to reject it. That's got it. That should be that one right there. If we construct a 95% confidence interval that does not contain the hypothesized value, we talked about this a lot today earlier, which of the following statements is true? So if the value is not in the interval, we can reject that value, and then the alpha level on the two-tailed test, I wish it said that, would be 0.05. We talked about this earlier. I don't know if we have a worksheet up with it, but the outside of it, think of this, here I can draw it really quickly. We got enough time. So if we have a 95% confidence interval, it's not quite, but we'll pretend that's 95%. If we have a 95% confidence interval, on the outside of it, on the two-tailed test, would be 5% alpha. And so 0.05 or 5% alpha. So we could reject it at the 5% alpha level. So we can reject the value at the 5%. We can reject it. It does not contain it. So it would not be an interval. We reject that value. And we did that a lot with the jump outputs earlier today. Check out that part of the video. Type 2 error is made when what? A type 2 is when the null is false and we fail to reject it. So let's just check. A type 2 is when the null is false and we fail to reject it. Jacob, did you get it? Did you get that 100? We did a few different versions of the questions, and hopefully we did some good ways to memorize the answers. A type 2 is when the null is false and we fail to reject it. That should do it right here. We're going to jump back into some D2. We got this. Let's hop over the main screen. And if you're looking for some more versions of that, we did some other ones during office hours, so maybe I didn't do every question, but write those down on note cards and make sure to memorize. A type 1 is when the null is true and we reject it. A type 2 is when the null is false and we fail to reject it. Good practice right there. Get those hundreds, more hundreds, and then you get a little bit of wiggle room for the test. Got some 320 coming up right here. 320, 2D. Question 2. Part D. Let's write an implicit regression equation. Let's do it. Here we go. Write an implicit regression equations. Stat 3 BS 320. Let's do this. So when we write a regression equation right here, it says, what is the implicit regression equation relating sales to ads for small products that go in the office? So we actually need to take this output right here and translate the full output. I wouldn't recopy. It says eval equals false. Don't do what I'm about to. I'm just putting it here so I can see it. I'm going to write here full equation. You don't need this. The full equation is not needed. And the full equation is going to be the intercept. So you just take the intercept and delete it down. We'll keep decimals on. The full equation is going to be the intercept plus ads times the x variable plus, you know what we might do? It's on a separate line right here. It's going to be pretty long. I'll put a thing there. So we'll do predicted sales. The y variable equals to intercept plus coefficient times variable plus, and this is a minus because it's minus, coefficient times variable plus, and it's doing those. Yeah, so maybe I need to. It's thinking I'm doing LaTeX writing, so you know what? Watch this. Magic. Now it's going to put it as an equation right there. And then we need to do coefficient times variable plus coefficient times variable. Okay. So does this process, got that 100? Awesome. Matthew, does it make sense what I've done right here? That to write this equation, I had to do the intercept plus the coefficient times the variable plus the coefficient times the variable plus the coefficient times the variable plus the coefficient times the variable. You're just adding all these together. This plus this times this plus this times this plus this times this plus this times this. We predict the sales are equal to the intercept plus this times this, and there's a minus because it's minus, plus this times this, plus this times this, plus this times this. You just go through and just multiply them together. So now, how could we solve this for just, it makes sense? Awesome. So it's just this plus this plus this times this. Once you see, you're like, oh, you just do this plus this times this plus this times this plus this times this. And now it says, what are the sales for products that go in the office? So what will I plug in here? Let's write out the equation that we're looking for. So the equation we are looking for is the equation of small products office. So small / office. So what will office become when I solve this? We're supposed to solve it. 100% supposed to solve it. So we're looking for small products that go in the office. What will office become? So this is a product. We're going to say this is a product that goes in the office. So I'm not going to solve the full thing. You want to reduce after I do this. So what will since it's an indicator, what will go into where I say office? Like room office will become a what value? What will we put in for room office? That will become this value when we solve it. Indicators can only take on one of two values. It'll either be the value or it'll not be the value. So since it is used in the office, it'll become a what value? So if something is the indicator value, like this is a office product, so then it'll become a what? Since it is something for the office, we will plug in what value for it. We're saying like, this is for the office. So let's plug in a what value. Indicators only take on one of two values. It either is the value or it is not the value. So since it is a product for the office, we'd put in what for the indicator of office? 1. Yep. It is going to be an office product. And then what would room kitchen become? Because it's not a room kitchen value. It's not room kitchen. Like this is not a product for the kitchen. So since this is not a kitchen product, that indicator will become what? So that indicator, since it's not, boom. And then this is a small product. Great job, Jacob. Yep. And so indicators just indicate if it is this or if it's not this. And so now, since it is a small product, we'd plug in this. And now mathematically, what are you just going to do to this equation? 100 points, everyone following along right here. What are you going to do to this equation? Now, all you have to do to this equation is what? Just take the equation and do what to it? Because this will be 0. There's that. And that's going to turn into, because if you reduce that, that's just that. And this is going to turn into this. Oh, there's a 1 right there. Move that. Simplify it. Yep. But watch this. Here's the confusing one. And we'll end on this because I don't know if we asked for this one, but what about large product? Wait, here we go. So what about products that are large products for the bedroom? Like a bed. That's what we're talking about. We're selling products right here and we're predicting the sales of these products. So wait, is it for the room office? Is it for the room kitchen? Matthew, why don't we see room bedroom? So we don't see a product that's for the bedroom right here. So what do you think I should plug in for room kitchen and room office? Because it's not a kitchen product. It's not an office product. So what do you think I should plug in right here for these values? This is the easiest one to solve in a moment. So it's for the bedroom. So the room it's used for, we're selling beds right now. It's a large product. Beds are large. So we have a large product sold for the bedroom. And so what should I plug in for room kitchen and room office? Because it's not a kitchen product. It's not an office product. So I should plug in what for both of these? For both of these indicators, since it's not them, and this means it's the reference level. So for both of these, I'd plug in what? 0. Exactly. Plug in 0. And then size small, is the product a small size? No, it's not small size. So we plug in a 0 here, indicating it's not size small. And guess what? When you reduce this down, we just solved out the implicit line because these are all zeros. There's the implicit line predicting sales for large products in the bedroom. And this is not the answer to the question we're working on currently, but if the question were to say, like, write the implicit line for large products being sold in the bedroom, predicted sales of large products in the bedroom are equal to $3.24 thousand. These are all in $1,000 plus 0.9694 times the ads. So this would be the predicted sales there. And make sure to reduce this down. This will change the intercept right here. Like the intercept will change. Like this has ads on it, so you can't combine these, but all of this will change the intercept. Is that making more sense, Matthew? How to take the full equation? We're looking right here at taking the full equation and writing different lines. Like, what about if it's a small product for the office? What about it's a small, just the intercept and ads? Got it. Yeah, and then the ads coefficient for all of these, since there's no interaction, this will not change. This will not change. The intercept changes right here because these are the differences we observe. This goes back to the rain, no rain problem, Jacob, we did way earlier on. It's the same sort of idea that the model will change the intercepts of the lines right here, but they'll have the same slopes, which means they would have the same coefficient of ads right here. Like the coefficient of ads won't change. Great job, Matthew. Matthew, swing by anytime, especially for the last few assignments. Swing by and be like, hey, Brian, can you work this? Great job, everybody. Great questions, great answers. We'll be back here tomorrow. Going to teach here in 14 minutes. 13 minutes. Bye for now, everyone. Bye. 2 minutes. Teaching soon. Now we have my voice on the thing.